So we were discussing natural convection. And we were just interested to look at the form of the Navier-Stokes equation which we can have. So the Navier-Stokes equation, generally we can write it like this: u partial u by partial x plus v partial u by partial y equals minus partial p by partial x plus mu partial square u by partial x square plus partial square u by partial y square. And there should be a source term as well. Why? Because I have already explained in the last lecture that in natural convection the fluid goes up due to the density difference, and that density difference is basically something creating a force which is going against gravity, and that could only happen once you put the fluid inside a gravitational field. So there must be a source term, and that source term would be kind of a gravity thing. Okay, that source term would be a gravity force. Now in that case, if we just look at the plate, look at this plate, because the fluid moves up against the gravity, so that is why there was a negative sign. Okay, the fluid moves up, so that is why there was a negative sign. So I would just say that instead of this source term, you can put minus rho g over there. Okay, so this is basically to look at the lifting of the fluid in the upward direction. Now the problem comes in, what about this pressure term? We were interested in this thing. So let me just write down the y part of this Navier-Stokes equation first. So y part of this Navier-Stokes equation would be and should there be a source term, by the way? There should not be. Why? Because in the x direction fluid is moving up. Y is basically normal to that plate. Y is normal to that plate, you can see that. So there would be no movement in the horizontal direction of the air. So we would not, or you can say there is no force applied by the field on the fluid in the horizontal direction. So there would be no source term in this case. So because we have already said, we have taken assumption that in natural convection, this is kind of, although it's a complex structure to talk about, but still u is much greater than v. Okay, similarly partial v by partial x and partial v by partial y, they are almost zero. Okay, so if we use those assumptions and put all the values over there, you would come up with this conclusion that there is no variation of pressure with respect to y. So if pressure is a function of x and y, and from this equation you know that there is no variation of pressure with respect to y, so pressure would just be a function of x, right? Pressure would just be a function of x. Now that was the point. So it means, coming back to this figure, if at any x location, just see, I am just making a section at x, whatever the value of pressure over there, which I represent as P infinity. Why P infinity? Because this point is outside the boundary layer, and if I just look at the pressure over there, these two should be equal. Okay, these two should be equal. Why? Because from the y part of the Navier-Stokes equation we have already said that pressure is not a function of y. Okay, so as you move up, let's say if this value is P1 and this value is, let's say, P infinity 1, and this is section 2, so at this point this value would be P2, something different from this one. Why? Because pressure is varying along x, and this value is, let's say, something different, but along this line pressure would not vary, right? So that was the point. Now how can we represent this thing? This is the question. This partial P by partial X, how can we represent this thing, partial P by partial X? Now see, if I just look at the outside fluid, the fluid which is outside the boundary layer, so I am just talking about the fluid outside the boundary layer. Now what is you can say a simplification for the fluid outside the boundary layer? U is almost 0, V is almost 0, isn't it? And we would use a word, I hope I would spell it correctly. Yes, you can call it a stationary fluid, or let's say you would use a word quiescent fluid. Quiescent means inactive. Okay, I am just talking about the fluid outside the boundary layer. For example, there is a natural, let's say if I just look at this room and you put all the heaters off, right? So, and let's say there is, for example, from your own bodies there would be some natural convection. You understand that? And that natural convection current, I would use the word flow due to the natural convection as natural convection current. I hope you understand the word. So natural convection current, this is a technical word which I would use. Natural convection current. If this is an object, you would see that the air would try to go up. If this is a hot object, air would be trying to go up, which is in the vicinity of this object. If you look at something over there, would there be any activity in the flow? Not at all, because there is no primary mover of the heat, is basically not being transferred to that fluid. Even if it is very low, and there is no considerable motion of the fluid, which is basically beyond a certain length, and I would consider that that length is kind of a boundary layer thickness. Okay, so beyond boundary layer thickness there is inactive fluid. In technical terms you can say it is a quiescent fluid. You would generally see that kind of word. So that is why I have used this assumption. Now let's apply what was the Navier-Stokes equation. Partial u by partial x plus v partial u by partial y minus partial. Now I would use the word infinity. Why? Because I am talking about something which is outside the boundary layer. Okay. So remember, this is not the free stream condition which we took in case of external force convection, but this is just something which is outside the boundary layer. So this would be minus p infinity by partial x plus mu partial square u by partial x square plus partial square u by partial y square minus, and I would use the word rho infinity as well. Okay, why? Because we are talking about the fluid which is outside the boundary layer, so that is why I am just using the, and this is different from that free stream kind of condition which we took earlier. So just tell me, all of those terms would be gone, right? And what you get out of it is equal to partial p infinity by partial x equals what? Minus rho infinity g. Okay, so from the previous equation, this one, you understand that p of x of y is basically p is just a function of x. So what I can write from here is that partial p by partial x should be equal to partial p infinity by partial x. I have already explained it. You understand it? Okay, so it means partial p by partial x equals partial p infinity by partial x, and that is equal to minus rho infinity g. So let's plug this value back into the previous equation. Sorry. you are talking about the equivalence of those two terms. Yes, equivalent height, right? And that is coming from what? The application of the y part of the momentum equation, where you see that partial p by partial y was 0. So it means pressure is just a function of x. Okay. So by the way, there is an interesting difference. You should understand that. I am taking an example of a vertical plate here, not a horizontal plate. But in case of force flow, external flow, we took an example of horizontal plate. So there is a difference. Why is it so? By the way, this is something related to common sense, and I will talk about it after a short while. So partial p infinity by partial x would be equal to this thing. So let me write down the Navier-Stokes equation again. U partial u by partial x plus v partial u by partial y. And now this thing would be what? Minus p infinity g, because partial p by partial x has come to this point. Yes, it should be plus. Why? Because this would be minus p, so it would become plus. So this thing. And finally you would get rho infinity minus rho into g. So you can say that this is the density difference causing the natural convection current. Yes, it should also be there. Thank you. That viscous term should also be there. Okay, so this is the density difference. Now see, because we are treating everything in the domain of heat transfer, we want to see how this density difference is related to the heat transfer. So what we need to do is we need to transform this relationship into something which can be described in terms of temperature. Okay, so what I wanted to see, that I want to describe this thing in terms of temperature difference. Okay, so how can we relate this density difference with the temperature difference? Come on, we talked about a quantity. What was that? Okay, that was volume expansion coefficient. You remember that? So let me just write down the relationship. This rho infinity minus rho can be written as rho beta T minus T infinity. So that was something from definition of beta. And what is this thing? Volumetric expansion coefficient. Right. Now let's plug this thing back into the equation. This would be rho partial u by partial x plus v partial u by partial y So this is rho u partial u by partial x plus v partial u by partial y, and that would be equal to mu partial square u by partial x square plus partial square u by partial y square, and then you would have plus rho beta T minus T infinity. Now the question is that there is some term for temperature as well. Yes, it should be G as well. Thank you. So rho beta T minus T infinity. So you see that there is a temperature term now. Now to get this temperature, you have to solve the energy equation as well simultaneously. In case of incompressible fluids, I told you that for incompressible fluids, you can solve the continuity and momentum equation simultaneously, and you can solve the energy equation later on. You don't have to solve the energy equation simultaneously with the continuity and momentum equation. Why? Because there was no temperature term in the momentum equation. Now you see, why do you solve all the equations simultaneously? Because all the parameters are available. Let's say x plus y plus z, 2x plus y minus z, right? So those kind of things are there. And there is something where only you have z. Okay, so you can solve, let's say some terms, let's say if you have x plus y and x minus y equal to something something, and then you have x plus y minus z equals something. So in the above two equations, you have x and y, so you need to solve them simultaneously. And in the third equation, you have z separately. So you would solve it after solution of the first two equations, right? So this is the case for incompressible fluid, that in case of incompressible fluid, which we talked about earlier, there was no temperature term, there was no source term. So you don't have to associate all the things with the energy equation, but this time you have to associate all the things with the energy equation. This is kind of a conceptual point, so you need to understand that if you are talking about natural convection, you cannot dissociate energy equation from the rest of the two and solve them independently. You have to talk about all the equations simultaneously. So this is the point. Now the thing is that if we have rho b beta t minus t infinity g, we are habitual of looking, this is basically dimensional form, isn't it? This is the dimensional form of the equation. Right? So we are habitual of looking at the things in the non-dimensional form. And you know the advantage. What is the advantage? We can simply look for the similarity parameters. Because while doing experiments, that can reduce the parametric space for the experimentation. Okay, you already know that, we have talked about that. I hope you remember the Buckingham-Boyle theorem and all that. So just look at these few terms. I explained this non-dimensionalization procedure earlier. Just see, if you take those reference quantities and plug those reference quantities into the Navier-Stokes equation, the x part, we are interested in the x part Navier-Stokes equation. You see, this is the characteristic length. Remember that this characteristic length is not about the flat plate length only. That would vary, that characteristic length would vary, and it would dependent on the geometry, right? And what kind of geometry? Even if you gave a small inclination to the plate, this characteristic length would change. Okay, so it is very important to see that this characteristic length, it is even determined by the experiments. So it is not that straightforward to write down the characteristic length as something equal to the length or diameter of the body. Okay, so you would see, I would show you few relationships, and those characteristic lengths are again part of the correlations. So once you use these parameters for non-dimensionalization, this is what you get out of it. You see, there is the Reynolds number thing. And this number is known as Grashof number. Okay, this number is known as Grashof number. G beta Ts minus T infinity L C characteristic length cube over nu square. This nu square is the kinematic viscosity, and it is being multiplied by T star over Re square L, right? Re square L. So this Grashof number is kind of the similarity parameter for natural convection. So you can say for Grashof number, this Nusselt number, or let's say the velocity profiles, they would be function of the Grashof number and Reynolds number. Now the situation has become a little complex, little more complex as compared to that in forced convection. So now for natural convection, what is the importance of this Grashof number is, if its value is 10 raised to power 9, if its value is 10 raised to power 9 and less than that, you would consider your flow to be laminar. You would see nice streamlines. And if it is greater than 10 raised to power 9, you would see that the flow is turbulent. Okay. So just see what is, just like you said that Reynolds number is kind of a ratio of the inertial forces over the viscous forces. What do you see over there? This Grashof number is kind of the ratio between buoyancy force over viscous force, isn't it? This is something which is buoyancy, this thing, G beta Ts minus T infinity, this is something related to buoyancy. So buoyancy over viscous forces, this is kind of the physical interpretation of the Grashof number. It shows you some comparison of both of these quantities. Any questions so far? Not Grashof number. So in natural convection, you would not define the laminar and the turbulent flow based on the Reynolds number. You would define it based on Grashof number. Okay. What kind of thing? Okay. Yes. If the Grashof number is greater than 10 raised to power 9, let me write it down over there. If the Grashof number is raised to power greater than 10 raised to power 9, then you would say it's a turbulent flow. And if it is less than 10 raised to power 9, you would say it's a laminar flow. So here you are not defining the flow regime based on the Reynolds number, you are defining it based on Grashof number, remember that. Okay. And why is it important? No, you have to consider that Reynolds number as well, because this is a similarity parameter. But once you do the experiments, you would see that Reynolds number is kind of not affecting the flow regime. And it might be very low, you can say. Reynolds number may be very low. But still you can see certain variations in the flow regime. There can be some transitions, then the flow may be turning into small eddies. Okay, and this is something associated with the Grashof variation. This is not associated with the Reynolds variation. Okay. Now let me tell you. Okay, did you remember about the things about Buckingham Pi theorem? We have so many parameters, and then you find out what? Through a certain set of rules, by fulfilling those set of rules, you come up with a few pi products. Okay, so instead of, let's say, 5-6 variables, you come up with 2 pi products or 3 pi products. So that's what I meant by reduction of parametric space. Okay. No. Simultaneously solution means that you cannot solve any equation independently. Let me write it down over there. For example, if I ask you to solve this x minus y is equal to 2, I don't know whether you would be able to solve it or not, but I am just writing it down. And you would have x plus 2x plus 3y plus 5z equals, let's say, 15. How would you solve this system? Yes, you need to solve these two equations simultaneously. And after finding the value of x and y, you can solve it independently. And still it is your choice to solve it or not. Now it has become a choice. It has not become a compulsion. But if had there been any parameter associated with z over there, let's say, now it has become a compulsion. You understood that? So that's why if some of you might have used Fluent, for any kind of simulation or CFX, or if you are having a course on Fluent, let's say in the next semester or next to next semester, you would see that once you select the flow to be incompressible, it would ask you whether you want to solve the energy equation or not, right? And if you do not want to solve the energy equation, you would keep the box unchecked. And if you check the box, it would solve the energy equation for you after it solves the continuity and momentum equation. Okay, so this is the reason behind it, right? Now my point is, why are you yes, reference velocity. This reference velocity, yes, this is a tricky question. Let me think over it and I would answer it. Once it comes into my mind, I would answer it. Okay, but please don't forget this question. Okay. So my point is, why are you looking at those all structures? Nusselt number, turbulent flows, you might be seeing those applications. This is not related to you can say the flow outside the environment and you are sweating and you just want to dry you down. Okay, so this is not the case only, but what you see is, if you are working in an electronics industry as a mechanical engineer and you want a heat transfer mechanism to cool down your electronic equipment, okay, so because it is an electronic equipment and you cannot install so many fans and so many pumps inside that. Let's say just consider a personal computer or just consider a laptop. What you have is, although you have a fan installed in that in today's computers, but let's say in previously you would prefer not to install any kind of fan. Why? Because to run that fan you need electrical energy, more and more electrical energy, which can, you can say, enhance the cost, right? This is the major parameter. So your choice would be, as a mechanical engineer, while you are working in some electronics industry, your choice would be to use the natural convection mechanism to keep your equipment cool. Okay, so this is something where you need to employ the rules which are related to the this natural convection. The second thing is, it is also associated with something related to the air conditioning of the buildings. How is it? For example, just look at the window pane. Although you have put all the heaters on, still if you just put them off, you would see that suddenly this room would start cooling down, isn't it? So all the heat would be going outside. Why is it so? Because you have, although let's say there are walls, but there are windows as well. So there is a good amount of chance that the heat would be transferred to the outer environment by the windows, isn't it? So if you somehow or the other you install some kind of insulator in the window, you can reduce that heat transfer and you can keep the room warmer for a longer time, and that would reduce the air conditioning, or let's say the cooling load of that building. Okay, and that ultimately that would reduce the cost as well. So finally everything converges to the cost, remember that. Okay, you need to save the money. So if you are talking about this thing, what kind of insulator you can install in your windows? And remember, windows are also there to see through. You want to see through those windows up what is going on outside, isn't it? So you have to keep these things in a way that what should be the appropriate material which can be used as an insulator in the windows. So you might be seeing those double pane windows. Have you seen those? So what's the advantage over there? The advantage over there is they trap the air inside those double pane windows. So air is the best insulator. Air is the best insulator. It would not let the heat pass through it, but obviously there would be some heat pass through it. What is going on in that kind of double pane windows, I would show you, but just to tell you what is the actual application of these principles which are being studied in this lecture. So you would see that air is there and you can see through the air as well. It is transparent, right? So instead of putting some solid material which can insulate this process, you trap the air inside it. Okay, and once you trap the air inside it, you see it's a design process, complete design process, and this is related to the energy efficient buildings as well. You might have heard that term from one of our colleagues, Dr. Imran. So he is working on that energy efficient buildings, and this is something which is very important to study, that if you have those double pane windows, obviously heat would be transferred to the air which is being trapped in those double pane windows, and obviously that air would start moving up, isn't it? If there is some air, it is getting heat from inside the building, it would start moving up, but it would remain within that space, right? And finally what you would see is that air would also start circulating inside that double pane window. Okay, and due to that circulation of air, because velocity is going to increase, convection is going to increase, and obviously it would try to extract the heat from inside the window and send it in the outside environment. So you need to keep that space, you need to select that space or design that window system in a way that you can reduce the heat transfer from the building to the outside environment. And the same is the case for some structures related to solar characters as well. Solar panels, you might have heard about this term as well. Solar panels, solar cells, solar character system. So they are there. This natural convection application is there. So you have to be very careful about the selection of these things. And the second thing is, I would also talk about the employment of this natural convection correlations for PCB designing. Let's say. Now, for example, if someone comes up, some electronic engineer comes to you and he says that, okay, I am going to give you this kind of structure. Just look at the figure which is on the right side. So those small circuit boards, they are there. Now tell me, which one is the better choice for natural convection? Upper one or the lower one? Come on. Upper one or the lower one? Upper one. Why? Why? Upper one, why it is the better choice? Yes, it can give you a good amount of flow rate, right? The circuits are, or you can say the surfaces are not closely packed. So it would let the air pass through it with, you can say, with more mass flow rate. But what's the advantage in case of second equipment? It would provide you more surface area, just like the fin definition. You remember that we talked about those things in the fins. So what do those fins do? They basically provide you more surface area, and you can have, let's say, more heat transfer if you have more surface area. But the thing is, this lower configuration, that might not allow you to, let's say, to pass more and more fluid through it. So you can say if you have more surface area, you would have more friction as well. Do you understand that? So you would have more friction, it means air velocities would be smaller. So if air velocity, you are increasing the area to enhance the heat transfer rate, but actually what does it do? It is reducing the heat transfer rate. So what you need to do is, you have to go for some optimum configuration. Remember that. You have to go for some optimum configuration where you can deal with all of these things. Okay, so this is the application of all those correlations and all those theoretical things which we are going to study, right? So just keep this thing into your mind, that a huge number of applications are there related to this natural convection. It is not about simply solving these Navier-Stokes equation. But the thing is, again, a very important point, that if you talk about this flow around this circuit, let's say, can you solve it analytically? Analytically means, can you talk about its boundary? Although you can, yes, you can say this is the boundary condition, but once you solve it and you try to find out its exact solution, you won't be able to do that. Why is it so? Because the geometry is very complex and the flow is very complex. You cannot take those kind of assumptions that V is equal to 0 and U is equal to something which is much greater than v, partial v by partial y is zeros. You can't do this thing with those geometries. Why? Because these are complex geometries. You cannot even solve let's say you cannot find out the exact solution for flow over a cylinder. So how can you do that for these complex configurations? So what you do is, either you perform the simulations through CFD, the solution of those partial differential equations, continuity, momentum and energy, or you go to experiments. Okay, and for those experiments you do all those things related to natural convection based upon two similarity parameters, which is the Reynolds number and the Grashof number, I told you. Okay, so in case of and now we are going to talk about the variation of the Nusselt number. Most of the time these relationships are what? Empirical, experimental. Okay. Now these empirical and experimental relationships for natural convection, they are of the form, yes, it's the same thing. It's the same thing, right? Empirical is something which is basically you have found out the values for a certain set of parameters, and then you have do the curve fitting thing with those data points, and you come up with this relationship. Okay, so let me tell you that those empirical relations are generally of the form of this thing, C Grashof number L, because we are talking about the total average quantity, we are not talking about a local Grashof number. Grashof number and Prandtl number N. So for Nusselt number, this is a function of what? In case of force convection, you did not have this parameter, you have those two parameters. Now you have this parameter as well. Okay, so generally you would see that Nusselt number would be dependent on this product. So this product is also known as Rayleigh number. Sorry? L is based upon the whole length, whole characteristic length. You remember we talked about the local quantities as well. What is the Reynolds number at this point? What is the Reynolds number of this point? Here you are not talking about the local quantities, you are talking about the total quantities, averaged, complete Grashof number. So this product is known as Rayleigh number, right? So generally you would see that this Nusselt number would be something of this kind. Okay. So you can see that this Rayleigh number would be equal to Grashof number into Prandtl number. If I just plug in their definitions of Grashof number and Prandtl number, this would be equal to G beta Ts minus T infinity characteristic length cube over nu alpha. This is the definition of Rayleigh number. Okay. So you have two constants over there. See, this is a constant, C is a constant, and this N is the exponent, and those two parameters depend on the geometry and the flow regime. geometry and flow regime, right? So you would experimentally determine them. So you can see that if the geometry changes, those two things would be changing. Sorry? Alpha is what? Do you remember this thing? Do you remember this thing? This alpha is what? Thermal diffusivity. Okay, so this is mu, which is the kinematic viscosity, then alpha. Any other question? Yes, geometry and the flow regime. They are experimentally determined values. Now this is the first case which we are going to talk about. Vertical plates. Let's talk about the vertical plate. Okay, so this is very interesting. Why did we, now let me answer that question. Why did we choose the vertical plate as the representation of this flow over a plate in case of natural convection? Why is it so? Come on, any answer from your side? Sorry? Sorry? Okay, this is related to this thing. Come on, be more precise. Yes, air needs to go up. Air needs to go up. So, did you ever try to, let's say, dry your hand, let's say wet hand, while putting on the heater of just like this? So, if the air is coming up, you would see that it would be trapped inside this area. And after, let's say, very quickly you would start feeling that it is burning. Why is it so? That your palm starts burning, literally. Okay, and but if you put it like this in front of the heater, still you feel comfortable, isn't it? So my point is that if you do it like this, you are allowing the flow to go up, isn't it? So this is the primary direction of the flow. But if you put the plate, just consider your hand as a plate. So if you put it like this, you are not allowing the flow to move freely. Okay, so that's the case that you take this vertical plate example in case of natural convection. So we have two conditions for the vertical plates. How many boundary conditions can be possible? Either you define temperature or you define flux. Okay, so there is a table given in your book which represents all of those correlations. Just see, this is the vertical plate, this is the range of, now see, characteristic length would also be given for all the geometries. In case of flow over a vertical plate, you would consider its length as the characteristic length. For this range of Rayleigh number, remember this is not Reynolds number, this is Rayleigh number now. And what is the Rayleigh number? It is the product of Grashof and Prandtl. So you would see, just see, what is the value of C over there? What is the value of N over there? 1/4. Okay. Now, is it visible to you at the end? Last man? No? Okay, let me write down the relationship for you. This first value is, can you see the plate at least? Okay. So this characteristic length is L, the length of this plate. Okay, there are three relationships, three ranges of the Rayleigh number. First range is for 10⁴ to 10⁹. If your Rayleigh number falls into this range, Nusselt number can be written as 0.59 Rayleigh number L raised to power 1/4. If the Rayleigh number goes from 10⁻10 to 10⁻13, Nusselt number would be equal to 0.1 Rayleigh number raised to power 1/3. Sorry? No, is it a Grashof number or a Rayleigh number? So remember, Grashof number is there, but you would define the laminar and the turbulence regime based on the Grashof number only. It has nothing to do with the Prandtl number. Okay. So, but for entire range, if you just want to find out a relationship which is independent of the range, this is the relationship. Let me write it down. This relationship is for entire range, this relationship is 0.825 plus 0.387 Rayleigh number raised to power 1 by 6 divided by 1 plus 0.492 over Prandtl number raised to power 9 by 16 whole raised to power 8 by 27, and then you take the square. Sorry, this is from here to here you take the square. This is equal to the Nusselt number. Okay. Now this is for the whole range of Rayleigh number. Yes. So this is complex, but it is more accurate. So instead of using those two relationships which give you simpler values, although they give you also the correct results, but more correct results can be obtained through this relationship. And just see, this relationship you get from what? Kind of a curve fitting technique on the data points for the Nusselt number which you have obtained. You cannot perform those experiments for the whole range of Rayleigh number. You do it for some ranges, you do it for some points, and then you fit the curve. So for this boundary condition, you can use the same relationships, although with some errors, but still, if you go for establishing the own relationships, it would cost you higher, but you can use the same relationship with some error. Okay. So you can use the same relationships as you use in case of TS. Okay, there is a very interesting point to think about. How can you define this heat transfer rate? How can you define this heat transfer rate? You can define it by multiplying this thing, Ts minus T infinity. Yes, because I have just chosen small q, so area is not there. Still, if you keep it a bigger q, larger q, capital Q, you can use the area over there. The point is, what Ts you should use in case of this Qs is equal to constant thing. What Ts should be used? This Ts should be temperature at the middle point of the plate. Those correlations, those experimental correlations, they would give you good values if you use this Ts to be the surface temperature. Where should it be? At the middle of the plate. Okay, and remember, still to find out this temperature, you go through an iterative process. It means that you start finding out that TL by 2 somewhere in the middle of the plate, and you would choose that value which fulfills these equations. Okay, so it is quite tricky. Again, remember that. Yes, for the first case it would remain the same. I am talking about the second one. Q dot S equals constant. I think you are confused with this arrow. I am sorry for that. Okay, so that Q dot S equals constant thing, the surface would be temperature on the surface would be varying, and finally you would come up with something. So my point is, what temperature should you use? this is the temperature which you should use. And it is not that straightforward to find out, okay, just find out if the length is 1, put some thermometer on, let's say thermocouple on in the middle of the plate, and you say that this is TL by 2. No, still you have to find out, you have to go left and right to find out the actual TL by 2 which should satisfy this equation. Okay, so remember this thing, TL by 2. Okay, still you can find it out, but the point is to find out Q dot S for the first condition. Do you feel any kind of difficulty? Not at all. But if you have Q dot S is equal to constant, then how can you apply this principle, Newton's law of cooling, right? So I answered this question by this relationship, that you have to choose the surface temperature, isn't it? But at what point? Because if you have Q dot S is equal to constant, temperature would be varying along the plate. Okay, so at what point you should choose your surface temperature? So my point is that through experiments people have determined that it should be TL by 2, somewhere in the middle of the plate. But still it is not that accurate that right in the middle of the plate you put some sensor and say that this is the temperature we are going to use. No. Still you have to go left and right a little bit. Okay. So that's why I wrote it down that through an iterative process you do it. Sorry? No, this TS would be showing you the whole surface temperature. Would it be showing you the whole surface temperature? It should be something on one point, isn't it? Generally, otherwise TS is a function of X. Okay, so let's talk about the case of a vertical cylinder. Vertical cylinders means what? Okay, so there is a condition. If diameter is much larger than 35L over Grashof number raised to power 1 by 4, if you satisfy this condition, use the relations for vertical plate. Okay, if you satisfy this condition that the diameter is much larger than this thing, so use the relationship for vertical flat plate. Okay, there is a very interesting case related to inclined plates then. Like for example, you might have seen that those fins on the motherboard, or let's say, sorry, in your PCs, they are placed horizontally most of the time, isn't it? Or in some system you might be seeing those in the vertical direction, vertically placed. So what's the advantage? I mean, you can see them just like this as well. They should be inclined. But what's the point? Just look at that. If you have a plate, which is a hotter plate, let's say, this is X direction and this is Y direction. I'm sorry, let me use this X and this Y just to keep the notation similar. For example, if the air, this temperature is Ts, which is greater than T infinity, the air would go up, right? The air would go up due to the density difference. If I just decompose the force, obviously it is going up due to buoyancy. This is the force, and it can be should it be theta? Yes, it should be theta. So it can be decomposed into two components, parallel to the plate and normal to the plate. Now you see that once the body was completely vertical, this flow tend to move along it. So it has got more surface area to transfer heat from the solid to the fluid. But if you make it inclined, the force which pulls the air in the upward direction and keeps it intact with the plate, that has reduced. You see that this velocity has reduced, this force has reduced, which is kind of f sine of theta, and this is kind of f cos of theta. So what you can see is that in case of external force convection, you said this is the boundary layer and you said that V is 0. It means there was no flow in the upward direction, isn't it? But in case of inclined plate, this plate, you see, can you say that the velocity layer would be of like this shape? Because there is some velocity in the vertical direction and some velocity in this direction. So what happens is that instead of having this beautifully shaped boundary layer, you would see that it would be making kind of plume, this kind of structures. The air would be going through this, and this structure you can say plumes. So those plumes would be formed, and no specific kind of boundary layer would be seen in those flows if you have an inclined plate. Okay, so if you see those kind of structures, and remember, you would see the same kind of structures for the horizontal plate as well. Just see, if this is the horizontal plate and Ts is much greater than T infinity, you would see that instead of having a good shaped boundary layer, you would see those kind of fluid would be going outside like this. And it would be circulating around it, and it would be going up then. Okay, so you can say that you would only have that classical shape of the boundary layer in what case? Vertical flat plate. Okay, and this is why you would have increment or decrease in heat transfer in case of natural convection. And the flow regime, flow configuration is completely different from that which you observe in internal flows or external flows for forced convection cases. Okay. Now let's talk about this thing, that if you have a vertical plate, what would you think about it? Whether the heat transfer would increase or decrease? Just tell me. It should decrease. Okay, similarly, if I ask you that you place a cold flat plate in a warmer environment, then can you think of this process? So these are the questions related to common sense. Okay, and everything is again that common sense also needs to satisfy the natural principles. So I mean, you have to think about it, that if you place a cold plate over there, how would the air move up, whether it would be trapped inside the region or not? Would it find any place to go through that plate, go over that plate? Is it there? So if you have more velocity, you can say that heat transfer would increase because of the convection principles, right? If you have more surface area, then you can say that heat transfer is going to increase. But this is not very straightforward to tell all the time that this is the general principle which is going to occur. Okay, so my point is that you should look at those conditions. You should understand that the flow configurations are completely different in case of natural convection for these kind of systems. Like this is a common question. For example, if someone asks you, why don't you place your sink like this? You should be able to answer that, isn't it? And that answer would not be coming through something which you have already learned in case of forced convection. You should keep natural convection in your mind. That if you keep the flat plate over there, would it try to increase the heat transfer or not? If you keep the plate like this, what would it do with the electronic equipment? Because if natural convection mechanisms, they are not properly designed, it would do what? It would heat the equipment and suddenly it would simply blow up. Okay, so it is the responsible of the mechanical engineer in any electronic industry to design what? A properly efficient heat transfer mechanism, and that too by which principles? The principles related to natural convection. Although, because we are talking about this thing, I'm just going to give you another hint. If you install a fan over there, there is a question. Why don't you install a fan as well? How much cost it would add into the electrical bill? This can be a question. So my point is, there is something related to ergonomics. Have you ever heard about this term, ergonomics? How do you place the things inside an equipment? Beautifully shaped so that it looks spacious and it fulfills the design requirements as well. Okay, so my point is that, okay, you install all the things inside your PC. You say that this should be the heat, let's say this is the position of the heat sink. You place all the fins in this horizontal direction, and your calculations say, okay, this is the optimum configuration which you can have. So how would you install the fan? Would you install a fan at the top of that PC or at the side? Why? Yes. So it means if you talk about something which is natural plus forced, there would be some flow due to natural convection which would be in the vertical direction, and there would be some flow from the forced convection, and that would be related to some primary mover of the fluid. Okay, primary mover of the fluid, which must be a fan in case of electronic equipment most of the time. So it should also give the assistive flow to the natural convection flow. For example, if natural convection flow is going up, you should install a fan over there so that it can send the air in the upper direction. If you install a fan over there, what would it do? So this configuration would be what? Opposing flow. And this configuration would be what? Assistive flow. And based upon this parameter, just see, we have a parameter of Grashof number over Reynolds number. Just see, isn't it? This is the Grashof number and this is the Reynolds number square. So Reynolds number is something which is related to the forced convection, which is taken as some representative of the forced convection. So what people say is that based upon this quantity, you can determine whether you need some assistive flow or some opposing flow, because this is related to natural convection, the Grashof number, and the Reynolds number is something related to forced convection. If it is 1, if this ratio is 1, oh I'm sorry, this is REL. If this ratio is 1, what would you think out of it? That the heat transfer rate which is being provided by the natural convection should be equal to the heat transfer rate which is provided by the forced convection. If it is greater than 1, sorry, if it is equal to 1. So you can say that, okay, fine, whatever you are getting from the natural convection, you are getting from the forced convection, the same amount. But if this number is, let's say, greater than 1, what would you say? That natural convection is stronger than the forced convection. If this number is lesser than 1, forced convection is greater than the natural convection. Okay, so you would keep this term into your mind, that how you can compare the heat transfer rates from those two mechanisms using this parameter, Grashof number over Reynolds number square. And where this parameter is coming from? The non-dimensionalization of Navier-Stokes equation. Okay. And remember this opposing flow and assistive flow configurations as well. Okay. Coming on to my point back. For inclined plates, let me show you the relationships. Yes. A primary mover is something which basically gives more velocity to the fluid. I am not talking about that primary mover which you might have heard about, let's say engines or dynamometers or things like that. I am not talking about that primary mover. I am just talking about something which gives more and more energy to the flow. Okay, just like the fan or the pump, things like that. Yes, it is kind of a boundary layer. It is kind of a boundary layer, but this is something which forms the edges of those boundary layers. You would not see a specific that classical shape of that boundary layer. You would not see that. Obviously, because that air needs to go up. Even if you look at this shape, just consider there is a cool air. It is going up just because of the temperature difference. It tries to go up, but it is trapped over there. Obviously, it would change its path. It needs to go back. Why? Because the air is coming from this side as well. And finally, they have to take this path to move up. Okay, so that's why those plumes are formed. Yes, it would be trapped. It depends. It depends whether this surface is cooler or hotter. It depends again. I was talking about a case where both the surfaces, top and bottom, they are at the same temperature. Yes, obviously, plumes would be formed on the both sides. But if one side is hotter and the other side is cooler, you have to look at those formations just considering the same principles. Okay. So, just see that for vertical flat plate, flat plate, characteristic length is again L. So just let me just read it down. Use vertical plate equations for the upper surface of a cold plate and lower surface of a hot plate. Use vertical plate equations, I repeat, use vertical plate equations for the upper surface of a cold plate and lower surface of a hot plate. Okay, and then replace G by G cos of theta. Replace G by G cos of theta. Okay, once you find that Grashof number, and that theta where those relationships can be applicable, the theta ranges from 0 to 60 degree. If it is more than 60 degree, fine, you can use the relationships of a vertical plate. You can consider the plate to be vertical. Okay. Sorry? I'm sorry.
So the theta is taken from vertical axis over here?
Yes. Yes, I'm sorry. Yes, theta is taken by the vertical axis. So just change the statement accordingly. Okay. If it goes beyond this point, let's say if this angle becomes 30 degree, consider it to be horizontal. Thank you so much for that correction. Okay. So similarly for this horizontal plate, if this is the hot surface, this top side is the hot surface, you can consider characteristic length as surface area over perimeter. This is the characteristic length in case of horizontal plate. And for 10 raised to power 4 to 10 raised to power 7, Nusselt number would be equal to 0.59 Rayleigh number raised to power 1 by 4. For 10 raised to power 7 to 10 raised to power 11, this is Rayleigh number. Nusselt number can be equal to 0.1 Rayleigh number 1 by 3. Right? And let's say from 10 raised to power 5 to 10 raised to power 11, there is another relationship which is Nusselt number equals 0.27 Rayleigh number 1 by 4. Okay, so you can see that if you change the regime, no complex relationships, only the values of C and N are changing. Okay. This is the example of the vertical cylinder which we talked about earlier. Then you have horizontal cylinders, where you can see those horizontal cylinders. Remember yesterday's quiz? Remember that if a pipe is basically transporting some kind of fluid through ice, or let's say some warmer fluid, what would happen? Right? And if there is no, you are talking about a lake, where is no primary motion of the fluid, just a lake is trapped over there, let's say, or a water reservoir is there. So obviously all the forced convection would be negligible. Everything would be related to the natural convection. Okay, and you can see those natural convection currents once you boil the water. Can you see it? Yes, those bubbles coming to the surface. If you look at the bowl in which you are basically boiling the water, you can see that those bubbles are coming up. Those are those currents, those movement of the bubbles, they are known as natural convection currents. Right? Remember this thing. And for spherical shape of the body, in this case, vertical cylinder, this characteristic length is length of the cylinder. In case of horizontal cylinder, characteristic length is diameter of the cylinder. And then if Rayleigh number is less than 10 raised to power 12, if Rayleigh number based upon diameter is less than 10 raised to power 12, Nusselt number would be equal to 0.6 plus 0.387 Rayleigh number D 1 by 6 over 1 plus 0.559 over Prandtl number raised to power 9 by 16. Okay, and this raised to power 8 by 27. By the way, you can see this relationship in your book. I am just writing it so that the person at the last seat can see it. Okay, this is kind of relation which you can have. For sphere, this Rayleigh number needs to be less than 10 raised to power 11, and there is another limit on this thing, that Prandtl number needs to be greater than equal to 0.7. In this case, Nusselt number can be equal to 2 plus 0.589 Rayleigh number D 1 by 4 over 1 plus 0.469 over Prandtl number raised to power 9 by 16 raised to power 4 by 9. So that was the relationship. So while describing all those relationships, I would also want you to go back and see what are the applications where you can see those specific geometries. It is quite straightforward to look at the few common geometries, but let's say where you can find out natural convection over sphere, where you can find out natural convection over vertical cylinder, or let's say the horizontal cylinder. I have given you one example related to horizontal cylinder. So please go back and check where you can see those kind of shapes in the natural convection. So this is something related to natural convection. From finned surfaces and PCBs. Now what does it stand for? PCBs? Come on. Printed circuit boards. Okay, printed circuit boards. You might have seen those preparatory kind of stuff from those mechatronics or electrical engineering students. Okay, they always try to dip those in acids or something like that, and then they pull it off and then wipe it, clean it. They try to see it like this. I don't know what they found it, but still. So this is something which you need to see, and this is something which is related to the actual application. You can see those finned surfaces in electronic equipment and computers. So quite common thing. So let me write down the relationships. That for Ts is equal to constant, I have already explained the flow regimes and the more and more surface area, the impact of more and more surface area on the heat transfer. I've already told you. So you have to come up with something optimum. Something optimum. Optimum means where you can compromise on few parameters, on all the parameters, but still you are getting the maximum performance. Okay. So for Ts is equal to constant, this Rayleigh number based upon the surface, it would be equal to G beta Ts minus T infinity S cube over nu square. Now by the way, what is this S?
Spacing.
This is the spacing between those fins. Spacing between those fins. Sorry, this one is the spacing. You see? This one is the spacing. I mean, those are the two fins, so this is the spacing between them, and spacing between those adjacent corners. Okay, so you can say that the Rayleigh number is not based upon this length or this width. It is based upon the width, the gap between those two fins. So this is how you define Rayleigh number for these kind of configurations. Or if you try to define Rayleigh number based upon the length, you would come up with this thing. How you can come up with this thing? If you just multiply it with L over S cube, just take it outside, go this length will go over there, so this would become Rayleigh number based upon length. So S cube over S cube is something like that. Okay, so L cube over S cube, I'm sorry. So that's how you can get Rayleigh number based upon length. So if you use this boundary condition, Nusselt number would be equal to 576 over Rayleigh number based upon the width S over L whole square plus 2.873 over Rayleigh number based upon the width S over L raised to power 0.5, and then everything is having an exponent of minus 0.5. Okay, so this is minus 0.5. Sorry? Yes, the vertical things. Why? Because if we keep them horizontal, okay. Now, there is another point, how we can find out the optimum spacing between those things. Because if you keep more gap, surface area would be increased. If you keep lesser gap, flow would be disrupted. Okay, so you need to look for something optimum. So that optimum width would be 2.714 S cube L over RAS, Rayleigh number, and to be more appropriately you can say 2.714 L over Rayleigh number L 0.25. So you should use this relationship. Optimum gap can be found out by this relationship. Okay, so if you are designing heat sinks for an application just like PCBs or something like that into computers, you should use this relationship for the optimum gap. And Nusselt number for this optimum gap, S optimum, Nusselt number would be equal to H S optimum over K, and that would come out to be 1.307. Okay. So this is something for a couple of fins. If you have more fins, just multiply their heat transfer with n. Okay. And all fluid properties are to be evaluated as at fluid properties to be evaluated at T average equals Ts plus T infinity by 2. Right? Now just the last thing of this lecture, let me write down the relationships for this boundary condition. Q dot S is equal to constant. Now this Q dot S is equal to constant thing, by the way, this should be more related to the PCBs. Do you understand why? Yes, it is trying to produce constant power generation, so it is trying to consume constant electrical energy, and that constant electrical energy may be converted into the heat as well. Okay, so that's why we use this kind of condition. So in that case, Rayleigh number would be equal to G beta, and instead of using the temperature difference, which is generally used for Rayleigh number, I would put a star over there just to represent the modification. You would use this thing, Q dot S, S raised to power 4 over K nu raised to power square, K nu raised to power 2 and into Prandtl number. You see that T minus Ts minus T infinity has been replaced by what? Q dot S over K, something like that, isn't it? Just see. So here Rayleigh number surface would be equal to G beta Q dot S, S raised to power 4 over K nu square. This K is the thermal conductivity. And in that case, the relationship for Nusselt number would be, the whole average Nusselt number would be 48 over modified Rayleigh number S over L plus 2.51 over Rayleigh number S over L raised to power 0.4 and whole raised to power minus 0.5. And in this case, optimum spacing could be found out by the relationship 2.12 S4L over this thing. Okay, and in this case, once you find out the heat transfer rate, all the fluid properties should be measured at TL by plus T infinity divided by 2. This is the temperature where all the fluid properties should be measured at. Sorry? For all what? No, I just took an example for Q dot S is equal to constant case, right? But if you have some other application, for example, you have installed fins on some other surface and you have constant surface temperature on the fins, then what should be the condition? No. Are you talking about that one fin case, that Q dot S is, that was only for the vertical plate. But if you have finned surfaces, I hope you understand what is finned surfaces. There are fins coming out of it, and those fins are having this boundary condition, you should use this relationship. That was for the vertical plate only. One vertical plate. Okay. for optimum S, not for all the gaps, not for all the gaps. For optimum value of that spacing, you have constant Nusselt number 1.307. That was the optimum thing you can get. Okay, the maximum Nusselt number could be in that case. You can say this thing. Optimum means either maxima or minima. In that case, it should be maximum. Optimum Nusselt number in this case. Okay, so how can you find out something optimum? Come on, as a function of S. Right? I've given you a general answer. You can find it yourself now, if you can. Sorry? Okay. So with the same approach, if you have S optimum, you can plug this relationship over there as well. Use S optimum to find out the Nusselt number. Right? If you have a constant value, that's fine. If you have some other number, you don't have to go for that differential. That I was just joking. Just look at this relationship. HS optimum over K. Simple as that. Okay. So, any question related to this thing?
TL is the whole length completely.
Or TL is the, yes, you can say it's the whole length, or you can just take the other point. Yes. Okay, the maximum point where the flow is leaving the surface. So we are done with most of the stuff in this chapter. There is just one thing left, the flow inside the window pan. Okay, we will look at the relationships, although I have given you you can say some concept related to it, but we would cover that topic in the next lecture, inshallah. Thank you.